Welcome to Math 365 PDE, doing a quick review of last time. And so, and compact support, you take that to mean that the support is a compact set that is strictly contained inside omega. So D is a vector space. We spoke about the definition of the dual space of any vector space, the collection of all linear functionals. There's some examples around that. Gave some examples of elements in the dual space of D for any L1 log function, for instance. You could define an element of the dual space to be that element where you take in element psi in D and spit out integral of u times psi over omega. So u is fixed and defines a linear functional on D in such manner, and therefore defines an element of the dual space. I pointed out that there are examples of elements in the dual space that are not just integration against a function. For instance, the evaluation function. The evaluation function evaluates you at the point x. And because of a book that Paul Dirac wrote 80 years ago, people call this evaluation function the Dirac delta function. Continuing the review, we defined the set of distributions to be the subset of the dual space given by not just linear functionals, but continuous linear functionals. And this is a distinction you don't care about for finite dimensional vector spaces. In that case, linear and continuous are the same thing. More generally, for a general vector space, if you're linear and bounded, then you're continuous. The reason why we wanted continuous linear functionals was so that you could take, so that you could have this property that if you had a sequence of functions in D, sequence of test functions converging to a limit, then when you take a fixed distribution and apply that to the sequence of test functions, that sequence of real numbers, u against psi k would then converge to u against psi. So you just want this property of continuity, and therefore you say that a characterizing property of a distribution is that you're continuous. Take any sequence, elements of D that converge to a limit, apply the distribution to that sequence, and the corresponding sequence of real numbers will limit to u against psi. And then we did this example of how do you multiply a distribution by a function. So for example, with Dirac delta, f times delta is just evaluating you not just at psi, but also multiplying by f of x. More generally, if u is a distribution, f times u is defined to be u applied to f times psi. Finally, we closed off the theory by saying that if you take a sequence of distributions, that sequence converges to distribution u if the following holds good, namely for every psi that's a test function, it holds that the sequence of real numbers, uk applied to psi, converges to u applied to psi. In other words, a sequence of distributions converges to a limit if the corresponding sequence of values converges as a sequence of real numbers, no matter what test function you pick. We gave an example of that. It's a classic example of a sequence of test functions that converges in the sense of distributions to Dirac delta distribution. So I took 1 over 2 pi e to the minus length of x over 2. I noted that this was a distribution via integration. And I also noted that I've scaled it, so its integral is equal to 1. I defined a sequence of functions f sub n, thusly. And we showed that this actually converges to Dirac delta in the distributional sense by actually calculating out Fn applied to psi. Looking at the difference between Fn psi and delta psi. And noting that that tends towards 0. Without showing all the analysis, but at least at this point you say, okay, well, as n is going to infinity, it makes sense that this quantity is tending towards 0. And of course, there's more details in your textbook on that. But I just wanted to show the example. Continuing the review from last time, we talked about how do you take the derivative of a distribution. So given a distribution, given a continuous linear functional defined on test functions, you would define the partial derivative in coordinate direction I in the following way. How does partial derivative in the coordinate direction I act on a function? It's defined to act on a function by negative that distribution applied to the corresponding partial of psi. Of course, in the special case that u is an L1 loc function and this pairing is actually integration, then this corresponds to the integration by parts formula. See me making that note. And more generally, using this notation, d alpha of u is defined to be -1 times length of alpha of u applied to d alpha of psi. Remember, alpha in this case is an element of Rn. It's telling you how many times to take a partial derivative in the corresponding coordinate direction. And so every time you take a partial derivative, you get another factor of -1. That's why it's -1 to the length of alpha. Almost getting us back up to speed where we stopped, looking at some examples of derivatives, right? So you look at evaluation function, you look at the distribution that evaluates you at the point A, say defined on the plane. The partial derivative of this in the y direction is equal to the negative of evaluating you at the derivative of psi in that direction. So take psi as an input, and the output is the negative of the partial derivative of psi in the corresponding direction evaluated at the fixed point A. Which makes total sense that the derivative of the evaluation function evaluates you at the derivative. And the negative sign is there as a leftover from integration by parts. Specializing further to n equals 1, we looked at function w. Function w when x is less than 0 is equal to -x, when x is bigger than 0 is equal to x plus 1. You define this function h to be equal to -1 when x is less than 0, +1 when x is bigger than 0. Define it however you want at x equals 0 or leave it undefined. Doesn't matter. We noted that h is not the weak derivative of w. We noted that w has no weak derivative. On the other hand, every distribution has a distributional derivative. Every distribution has infinitely many distributional derivatives. This example, this definition is always valid because psi will always be a test function, will always be able to be differentiated as many times as you like. That gave us the conundrum. There's no weak derivative, but what's the distributional derivative? So by definition, W prime applied to psi is equal to the negative of W applied to psi prime. And since the interpretation of W as a distribution is integration, this is, by definition, equal to W prime as a distribution applied to psi. Namely, it's the negative of psi applied to W prime, which is therefore the negative of the integral of W against psi prime. I asked you as an exercise to compute this integral. You split it up as negative infinity to 0 plus 0 to negative infinity. Apply integration by parts on each summand. Conclude that the answer is psi of 0 plus h times psi dt. And so this tells us two things. First of all, it tells us why there's no weak derivative, because you're not going to get this as integration against a function. And weak derivative requires integration against a function. Distributional derivative does not. Distributional derivative is what it is. That's the answer. And I recognize this as Dirac delta plus h, meaning that W prime of psi is equal to delta plus h applied to psi. Which is by linearity going to be delta applied to psi plus h applied to psi. H is a locally integrable function, so its interpretation as a distribution is by taking the product and integrating. So you can see exactly that this evaluates psi at 0, giving you psi 0, and the other one gives you h times psi and then integrate. So you get this formula for W prime as a distribution. Yes, it's true that W prime applied to psi by definition is this thing, but then we calculated it out to give us a nice formula we can actually use, that W prime is delta plus h. So that concludes the review from last time. Are there any questions on any of that? So that's technical enough that I thought it might be good to actually do a quick review, so I hope you don't mind that. So let's continue with another example. So this is called the Heaviside step function. Heaviside was an electrical engineer. So he's just modeling switching something from off to on, right? Of course, if you're a mathematician, you just write down the step function. You're not going to get it named after you, but the point is that Heaviside was using this in applications. So as an exercise / example, I'll ask you to show that as a distribution, h prime is equal to delta. And you can take a moment and even try to work that out, like as I'm going through the lecture. But this exercise is less difficult than the previous example. So it's like a further specialization. And therefore I won't show the details. But like doing this is really just checking that you understand the definition of distributional derivative. But it's a classic thing, and it's another example of a function that does not have a weak derivative because of the jump discontinuity, but it does have a distributional derivative. And since this is used so often in engineering, just doing engineering work basically requires you to understand distributions. Okay, and I'll note that in my last example, constructed it this way on purpose. So function W was actually Heaviside step function plus absolute value, because it was just equal to negative x. When x was less than 0, you're adding 0 to it. X bigger than 0, it was x plus 1. Previous example was Heaviside step function. So if you happen to know that the derivative of Heaviside is Dirac delta, and if you happen to know that the weak derivative, and therefore the distributional derivative of absolute value of x, was h, right? So absolute value of x, we saw this at the level of weak derivatives. When you take something that's discontinuous, but it's not a jump discontinuity, you can calculate its weak derivative and therefore its distributional derivative using this trick of looking at each piece and doing integration by parts. And since the boundary terms will match and then vanish, it works out. So noting that absolute value of x prime is equal to h in the distributional sense, and that h prime is equal to delta in the distributional sense, and using linearity, you could also figure out immediately that w prime is delta plus h without having to do any of the past work. So I could have arranged the lecture like that if I'd wanted to. Any questions or comments on that? So I hope that provides some good context of how to do that. You can actually go back and treat this Borthwick example of where he also uses discontinuous W. I believe you can actually go back and treat it in terms of like Heaviside plus whatever, or whatever. Oops, whatever the length of the jump is. Just scale this by a. So maybe it's like a times h plus whatever. Still be able to work it out with linearity. I want to treat another example that I think is pretty cool and leads itself to generalization. Let's look at the natural log of absolute value of x and ask what is the distributional derivative. So natural log of absolute value of x, this has this infinite sink at the point x equals 0. And so two things. Natural log of absolute value of x is in L1 log. So you take any interval from a to b and you can integrate natural log of absolute value of x over that integral. You saw that in your homework or in my solution to the homework. So because it's locally integrable, it defines a distribution and therefore has a distributional derivative. That's important. So you need to know in advance that you can differentiate this thing and you're not just fooling around with integrals that may or may not exist. But it does. And so here's the issue. So from calculus 1 that the derivative here, so long as x is not equal to 0, the derivative pointwise is 1 over x. So you might say that this is the answer. You might say that this is the distributional derivative given by the formula, plug in psi, and get psi over x on R. Problem is, it's not quite right for technical reasons. This does not define a distribution, as this integral typically doesn't exist. So 1 over x is not in L1 log. It almost exists, but it doesn't quite exist. So what's going on? Like, we need to be a little bit more careful and hew close to the definition. So the definition is so we know there is a distributional derivative. That much we know. And here's its definition. It's the negative of natural log of x applied to psi prime, right? And so this derivative exists precisely because this quantity is well defined. Since natural log of absolute value of x is L1 log, therefore general theory tells you you can multiply it by a smooth compactly supported function, take the integral over r, and this does exist. So then you try to calculate this. And this is like an improper integral because of the fact that you have this singularity at x equals 0. So what you do is you excise a ball of radius epsilon. In this case, you excise an interval of radius epsilon about 0. So you take the limit as epsilon goes to 0, negative infinity to minus epsilon plus epsilon to infinity. And you do integration by parts on each term. And, you know, I'll skip, I hope it's okay. Like, I'll just skip that. You do integration by parts on each one of these. And then conclude that it is the limit as epsilon goes to 0 of psi over x of the same thing. I just wrote it as absolute value of epsilon, you know, absolute value of x bigger than or equal to epsilon. And this might be confusing to you because you might say, like, you didn't do anything. Like, you just told me that this integral doesn't exist. Then you wrote down the definition. And you integrated by parts as usual and concluded that the answer is now, once again, psi over x. Integrate that over r. So like you're saying, Ken, you said this doesn't exist, and then you're telling me, actually, no, that's the answer. Well, not quite. Because you have to know a little bit about the definition of like Riemann integral. Because if you know in advance that the integral exists, then you can calculate it in this way by like sort of like symmetrically, right? By taking out a chunk of length epsilon away from 0 in the negative side and in the positive side, and then taking a limit. But if you didn't know for sure that the integral existed, integral exists if the Riemann sums converge, basically, no matter what partition you take. Basically, what I'm saying is, if you know they converge, then you can take this like particular partition where you're creeping in on the origin in a symmetric way. But if you're in a situation right here where it's not known to exist, then different Riemann sums will give you different answers depending on how you approach 0. So even though this integral doesn't exist, it is true that the Riemann sums do exist if you approach from the origin symmetrically, as I'm doing here, in such a way basically that you'll get some cancellation and you'll get a number here. And so that's called the principal value when you take out that ball of radius epsilon and then evaluate it and then take the limit. So it's quite subtle. If the integral existed, then the principal value would be equal to the integral. But 1 over x doesn't exist, but the principal value does. So that's why we had to make this definition. So the derivative of natural log of absolute value of x is not 1 over x as a distribution that doesn't exist. It is the principal value of 1 over x as a distribution. So if you go on into higher mathematics, you'll see people saying, take the integral in the principal value sense. Yeah, what they mean is just take away a ball at the singularity, integrate, and take a limit. But the reason why they're saying is you get into these sort of thorny situations where like you can treat this as a distribution in the principal value sense. You cannot treat it as a distribution just as the function itself. I know that's kind of technical, but it's a good example for why you want distributions to exist in the first place. And it illustrates some of the subtleties that you have to confront if you go on into higher mathematics, and you have to confront them in worse ways if you're in higher dimensions. So you get into this whole field of singular integral operators that some researchers in the back half of the 20th century got really famous for working on. People like Calderon and Zygmunt and Stein. But any questions on that? Okay.
Wait, Ken, could you do example 3 maybe at the end of class or something, or post an answer, a solution to it?
Like show the work for that?
Yeah.
Yeah, that's fine. If we have time at the end of class, then yes. Otherwise, I'll post solution. But do maybe I'll post a solution like a half an hour after class, because I want to give everybody a chance to work it out and check those definitions. Now I want to put a nice cap on the entire course. So we had been talking about Laplacian U equals delta, which didn't make any sense in the classical sense, where we were working on R2 on the entire plane. And U was the function negative natural log of R over 2 pi. And supposedly it's true that Laplacian of U is equal to delta. But what does that mean? Well, you can't even interpret this in the weak sense because delta is not a no one loc function, it's a distribution. So we would need to interpret this in the distributional sense. So now I want to show you how to do that. I want to kind of prove to you, relying on work that we've done in the past, but I want to prove to you that Laplacian U equals delta in the sense of distributions, and make it clear what that means. So consider again U equals negative natural log of R over 2 pi, with R being the square root of x squared plus y squared as usual. Our domain omega is R2. Therefore, D is compactly supported smooth functions on R2. And the space of distributions is continuous linear functionals on D. So I'll note that U is a distribution via the pairing U paired with psi is integral of U times psi all over R2. And I re-emphasize this technical point that like if U was 1 over R, maybe we couldn't have done that, although we're in R2, so it's a little bit different. But since U is natural log of R, this is a function that's L1 log. I've had you check that you can integrate that. Basically using the L'Hopital's rule that you end up showing that R times natural log of R has a limits to 0 as R goes to 0. So it doesn't make sense to define this as a distribution. And therefore, it makes sense to define the Laplacian of u as a distribution. I mean, Laplacian of u is one of these d alpha of, Laplacian of u is d alpha of u. I'll put this in the other notation, right? Where alpha is 2, because you're just doing du dx plus du squared dy squared. So in this case, alpha is in this case, alpha is 2, and its length is equal to 4, just to be really concrete. So I'm not just throwing something at you that you haven't seen before. We did make a definition for what this is in the sense of distributions. And what it is you take -1 to the 4th power, which is 1, and then just apply d alpha to psi, which is just, the Laplacian. So this is not like Green's formula or something like that. This is just a definition of what it means for Laplacian of u to be a distribution. Okay. And so then I claim that as distributions, Laplacian of u is equal to Dirac delta. And so what does that mean? It literally means that Laplacian of u delta, or Laplacian of u psi, is equal to delta psi, right? Laplacian of u psi, which by definition is u Laplacian of psi, but it's equal to delta of psi, because these two distributions are equal to each other. So they evaluate to the same thing when you plug in a test function. So this is literally what it means for Laplacian of u equals delta in the sense of distributions, means that Laplacian u psi is equal to psi naught. So this is something that I can actually prove, right? I can actually try to prove that the integral of u times Laplacian of psi over R2 dA is equal to psi naught. Everything well defined, because u just needs to be L1 log. That's the point. It doesn't need to be C2. The Laplacian appears on the smooth function. And I just need to prove that this is psi naught, and I'm finished. But we did do this with Green's second identity. And I'll just briefly indicate what we did. Because we first noted that, right, so Green's second identity is not used up here, it's sort of used in the proof. So we first noted that because it's true that Laplacian u equals 0 if r is not equal to 0, and because integrals don't care about the value at a single point, it's therefore true that 0 is equal to Laplacian of this times psi. And therefore true that, so v epsilon was R2 with a ball of radius epsilon removed. So therefore it's going to be true that 0 is equal to the limit as epsilon goes to 0 of this integral. And there's Ghost helping out. And now you apply Green's second identity. You still get the limit. You applied Green's second identity. And critically, the Laplacian moved over to psi, giving you the quantity that you're looking for, but you also got, Ghost's getting in there, but you also, he's trying to interact with my hand a little bit. So Green's second identity gives you a term that is what you want, and it also gives you a boundary term that as you take the limit as x goes to 0 gives you that average, gives you psi of 0. And then you concluded from that psi of 0 is equal to minus natural log of r over 2 pi times delta psi, which is by definition equal to Laplacian u psi as a distribution. So at the time, I promised that I would give an explanation for why my calculation kind of settled the issue. So this is my fulfillment of that promise. And so you go back and plug in, you know, the work that we did and refer to it, and you'll see this conclusion. And I literally went back and looked at the notes and checked it out so that, you know, there's no mistake and whatever. It really does work. Not just being the meme of skip the part where you get stuck and say it's trivial. So this is the wrapper around the nougat of mathematics that shows why this makes sense. And this justifies the existence of distributions, right? Because this whole thing came up as a physical problem where delta was interpreted as like a unit charge density. And it made sense. The physicists kind of landed on this equation, but had these mathematical problems because delta wasn't literally a function. And the way to resolve those problems didn't even happen until 100 years later, until the 1950s. The way to resolve that problem was to say, like, you can treat this as a distribution in this setting. And then with that setting, it is true that Laplacian u equals delta as distributions. So it's quite a remarkable achievement to invent distribution theory and completely solve that physical conundrum.